Good afternoon. It's Tapan Bagchi again. I resumed the talk on Six Sigma. This is a series of lectures that we have ready for you. And the specific topic that I'll be covering today is the analysis of measurement systems. As you all know, whenever we have to take a decision in regard to quality, we really make some measurements. And I have a device here. This is an electrical device, and it's supposed to be making some measurements that's relevant to us. And what it really produces is data. Most of our decisions are actually data-based. Most of the decisions in the assurance of quality or the management of quality or the control of quality, these are all data-driven, data-based. So therefore, we must have really good measurement systems in place in order that the data forms a sound basis for us to make our decisions. Unfortunately, in situations, most of the situations, the data is coming from the process into this system and then into the form of the data that we observe. Now, this system itself, it can introduce errors for us. And the idea of measurement system analysis is to try to take a look at the role played by the gauge and also the operator who is using the instrument in producing the data. And there are some methods that I'll be discussing today to try to make sure you eliminate from the data that you have, at least you have a good estimate of how much error is being committed by the gauge and how much it is committed by the individual, the operator. So we begin our lecture with the pointers today would be, I'll be giving you some idea about what is accuracy, what is precision, what is this phrase called gauge R&R, and we'll try to find an idea, we'll try to get some idea about how to go about finding that gauge R&R. It's a number that we find, and we always must have an estimate of this number in order that we can again make our decisions in regard to controlling quality on a sound manner. Now, measurement error, like I just said, these are considered to be the difference between the value that you observe, that you measure, and the true value of the item. That's what really is what measurement error is, and this would be there. It depends what kind of instrument you are using, of course, and who the person is who is making the measurement. Therefore, anytime you are using an instrument, keep your mind open about some possibility of some measurement errors being there. What exactly are we talking about? What we are saying is, we have all these tools in quality assurance. For example, we've got the expert chart, we've got the R chart, range chart. These are used in statistical process control. Then we've got the moving range chart, or we have the P chart or C chart and so on. These charts are used to control processes when they are online, when they are basically online. Now, creation of the charts is only as good as the measured data. This is very important for us to realize that unless you've got good data, the charts would give you wrong signals perhaps. Also, many times we're conducting design of experiments, particularly in the Six Sigma situation, under the DMAIC framework, in which there is one key element there that is called I, the improvement. And improvement is essentially based on, it uses designed experiments as the basis for coming up with factor effects and interactions and so on. And also it helps you to optimize the process. DOE is totally based on the data that you collect during the experiment. And there again, you'd not be collecting the data directly, you'd be coming through an instrument. You'd be coming through an instrument like this, only then you'd be getting your data. It's very important for us to realize, even if I'm doing an experiment perfectly well, my instrument must be such that I have an idea how much error is being introduced by this and also by the person who is using this instrument in regard to the production of the data that in this case, in this particular case, would be the observed data. Now, coming back to the slides again, measurement studies clarify all doubts about the validity of the measurement system, because we may have some doubts about the validity of the measurement system itself, not only in SPC charts, but also in DOE and any other statistical method that you'd like to use that is data-based. Let's take a look at this phenomena, these two phrases called accuracy and precision. Now, imagine that I've given somebody a gun, and this gun is then passed on to other people, and I ask them to fire at a target. Now, the bullseye is right at the middle. Each of these targets has a bullseye, that is the cross, that's right at the middle, and that's where they are supposed to be shooting. Now, this person, look at the shots that he has fired, is spread over a wide area. And some of the shots are even outside the specification limit, which is like It is outside the disk altogether. Now here look at this situation. The average of the shots, that average is shown by this green line. It is off target. The target is right there and the average is off target. This is the situation when I say that the system here lacks accuracy. It is not an accurate system. Also look at the wide spread, which is shown by this little bell curve here, which shows the distribution of all these shots. And again I say there's a wide distribution here that actually implies that this system here also lacks precision. Take a look at this system. This is somebody else using the same gun and firing shots. His average tends to be exactly at the target. So therefore, this system is accurate. But again, there is a wide spread in the positioning of these fires here, the shots here. Therefore, precision is poor. Look at this one particular person who has fired his shots very consistently in a very localized area, but he is off target. So here he is lacking accuracy because he is off target, but his precision is good because most of the shots are pretty close to each other. And look at this fourth person who fired his shots with pretty decent accuracy. The average is right on target, and also all the shots are very close to each other. So again, to review this, if I do not have good precision, I'll have wide spread in the data, and if the average is off target, I'll also be lacking precision. I may restore accuracy by cocking the gun slightly to the left. In that case, I'll be getting my accuracy, but if the spread is wide, I'll be lacking precision. I will be lacking precision again if the spread was wide, but this one particular shot, this third picture here, has good precision, but it's lacking in accuracy. And this fourth performance here has both accuracy and also precision. A measurement system also will suffer from inaccuracy and also poor precision. And we've got to make sure we understand how much inaccuracy is there and what we do about it, and how much precision is there, again what we do about it. It's very important for us to realize that. We've got to also understand the causes for such variation, wide variation, and why the shots are actually off target. And this is done to try to make sure you've done what we call measurement system analysis. If you do measurement system analysis, you'll have a pretty good idea of how your measurement system is behaving. There are a couple of things that actually happen when you are making measurements. There is, of course, what you really want to measure, and I show here that by showing that the process or the parts, they have their own variability. No two parts are exactly alike, and therefore you'll have a variance that will be based on the variation within the process itself. When I'm measuring the data, I introduce additional variation, and that is actually the measurement variation. So the data that I really observe, data is what I observe, it is the variance of this full data. It comprises the part variation and in part the measurement system variation. These two add up, and therefore I really have data that has got inflated variability. I would have really liked to get an idea of this, the true variation, part to part variation. But because of this measurement system error, I end up with inflated data, and that is actually something that is really misleading for me. So I must have an idea of how much this is as compared to the true part to part variation. What actually happens when you have a system or you have an instrument that is not doing a good job? What actually happens there? Suppose your true variation was, as I show here, the true variation is, I've got the upper and lower spec limits, and then of course I've got what we call the variation that is within the specification limit, well within the specification. So the true variation, as you see there, it is well within the specification limit. That is shown by this green letter there, and the blue letters that show you the range of the natural variation of the process. But when I introduce measurement errors, the data actually gets wider. The data will have a wider spread, and therefore the true value would look like this, but in actual fact it's smaller than this. Now, if I'm using a measurement system, I've got to make sure that I have an idea of how much this inflation is, and that is the variation that is introduced by the measurement system. Let's take a look at some of the components of what actually introduces variation, the additional variation due to the measurement system not being perfect. The first is, of course, the source of variation could come from the gauge itself. Or when I apply the same gauge, I take the same gauge and I use the same part, let's say some voltage that is coming out of a battery. and I try to measure that in the system here. The gauge itself may, gauge and the method of measurement, it may introduce some variation, and that is actually what we call gauge error or repeatability error. So, if I repeat my readings, I will find there is some variation in it. This is due to the gauge itself. A single person making multiple measurements will end up with that variation, which is the measurement variation. But there is another component that introduces error in the data. It is the person, it is the operator who is using this instrument, and that is what we call operator caused variation. So, in fact, if you look at the total data, there will be some part of the data that will be truly caused by the part to part variation. That is the true process variation that you are after. Then there is one part that is caused by the gauge. So, the gauge introduces some error because of the repeatability issues there. Then of course, the third component is the human being, the operator who is using this instrument and making the measurements. He puts the object there and he applies the gauge and he gets a reading there. There may be some errors introduced by the individual also. This is what we call reproducibility, and that changes person to person. If we keep moving here and if you look at this total picture, the overall variation is over here, and this overall variation is caused partly by the true variation in the part, and you see the little green bell curve there that shows the variation in the part itself. This is the true variation in the process. But the gauge itself will introduce some additional variation, which is the gauge variation. This is what we call repeatability. And then of course, the operator who is using the gauge, he also introduces additional variation, and that is called reproducibility. So, in fact, the total variation would be part this, which is the part to part variation, part the error that is introduced by the gauge, and part the error that is introduced due to the operator. These are the different sources of variation in the data that we measure. If you look at some of the terminology, now this has become a science, measurement systems analysis, it is a science, and what we have done is we have tried to understand what are the different terms that we have to study, what are the different aspects we have to study, and we have coined our own terminology here. The measurement systems people, these experts, they have coined their own terminology. First of all, there is something called discrimination. Whenever you are using a gauge, for example, the gauge that I have here, there is a least count, there is a minimum value. There is a minimum value that you can measure with this gauge. Of course, this is a digital gauge, so it is much better than the analog gauge that we had in the older times. But this itself would come with different amounts of different extents of least count. Least count is the discrimination. That is the amount of voltage, or there is the amount of say resistance or current strength that you would like to measure, that you can measure with this gauge there. So, that one particular input, the very first input is of course what we call the discriminating capability of the gauge itself. Then we got some term that is called the true value. True value is the theoretically correct value. That is actually the part to part variation. That is a true value of the data that you are trying to measure. So, if I get the cursor here, you would be able to see what that thing is. The true value is the theoretically correct value. Then there is something called bias. Bias is the difference between the average value of all the measurements that you have done and the true value for that sample. So, there is a difference now between the average that you produce as a result of multiple measurements and the true value. There is a difference between these two, and this is called the bias in the system, in the measurement system. Then of course, we have got something called repeatability, and repeatability is actually the issue of using the same gauge and basically applying the same gauge again and again. This would be done by the same individual. It will be done by the same operator, and basically what he will end up doing is he will apply the same gauge and he will end up with different readings, and those readings would be caused by the gauge itself, and this is the issue of repeatability. Then there is the issue of reproducibility, and that is actually the issue when we have different people using the same gauge and coming up with different measurements. That also is something that ideally we should really reduce. We should try to make that next to zero, and that is also something that we would like to make sure that we have an idea about. Then as you are applying the gauge, the reading today may be slightly different from reading next week or the reading a month later and so on. That is because there is some drift in the system, and that happens because of a variety of reasons. So, in fact, again, measurements that you produce, the data that you produce may have a drift, and the measurement system, if it has a lot of drift, then it is not a stable system. This is also a problem. Then of course, we got the issue of linearity. Many times what happens is, when you got the process in place, the accuracy or the precision, it may change over the range over which you are trying to make the measurement. So, for example, linearity can also be an issue with a measurement system that you are using. It's very possible that it's not linear in the full range of the measurements that are possible to be made with this gauge. That also is an issue that you'd like to take care of. So, discrimination, what is discrimination? You take any gauge like the gauge that I'm showing here on the screen there, it is the least count that will tell you, can I discriminate between two readings which are, at least it will be the least count of the thing that would turn out to be the least count or the discrimination of the object itself. And that would give an indication of what the discriminating capability is of this measurement system. There are certain things that are called systematic variation, and things that fall under that, those would be accuracy, and also those would be reproducibility. Accuracy I have already discussed, and the way to fix accuracy is when you do calibration. When you do calibration, you try to adjust for accuracy. That is like something that you do. Then of course is the issue of reproducibility, which would change from person to person. So there again, I've got to have some idea of what is the extent of reproducibility in the measurement system. Then is the issue of this temporal change, which would really give some indication about the wear and tear that might be taking place in the total measurement system, and that would give an indication of how stable the system is. Then of course, we've got some factor called the random variation. This is captured under repeatability. Now, when we look at a measurement system, we do try to get an idea of, is it properly calibrated? So, we try to get an idea that the system itself is accurate. It can provide, if I look at the average, it will provide me correct readings. Also, I'd like to make sure I have an idea of the reproducibility. This is a variance measurement. This is not an average measurement, it's a variance measurement. I also have a variance measurement when it comes down to repeatability, which is like repeat readings made with the same instrument. And of course, the issue of stability is also there, when the reading itself may change a little bit as time goes by. Let's try to get a good picture of what we are talking about. The observed value, I have a true value there. I have a true value there, which is the true average of the process. Then I've got this average value. This average value is the observed average value. The moment the average value differs from the true average, I say there is a bias in the system, or the system is not accurate. So that's an indication of inaccuracy of the system. Then you've got something called stability. If I make measurements at time 1, I get one distribution of data, and the average reading is at a certain point. When I make the same measurement, I measure the same object at some other point in time, again I get some variability due to gauge variation and due to the issue of reproducibility. But it turns out that the average also shifted, and this shift has taken place over time. This is an issue of stability or instability. This is also something that we'd like to get an idea of when I'm using a measurement system. Then of course, this issue of reproducibility. And like I told you, reproducibility is basically, it hinges on operators. So operator A has given me these readings, and the average is here. The true value is here, of course. Operator B has given me these values, and operator C has given me these values. And look at the difference of the averages produced by these three different people. And this difference here is attributed to what we call poor reproducibility of the system. People have a large effect in the actual data that is produced. Then of course, this issue of repeatability, and this is actually caused by all kinds of random factors that might be affecting the gauge. It could be some slight variation in temperature, gauging, positioning. So many things are there because of which the gauge may produce slightly varying readings, even if I measure the same current or the same voltage or the same resistance. That's also something that we'd like to get an idea of. Now, there is something very interesting, of course. In most cases, these different factors, one of which was reproducibility, the other was repeatability, many times these different factors, their effects do not interact. And that's a really, really good thing for us, because what it does is, it helps us, it allows us to utilize a principle that we learned back in high school, the Pythagorean theorem. And that actually says this, that the total variation, and I'm going to be repeating this several times, the total variation, I'm just going to call it C square, is the sum of component variation, one of which is A square plus B square is equal to C square. So this could be repeatability, and this could be reproducibility, and this is the total variation produced by the measurement system. Ideally, of course, what we would like is, we would like to have this to be reduced to 0 and also this to be reduced to 0, so that the measurement system itself contributes no error in the system. This is what we would like to be able to see. Now, can you really find a perfect gauge? It will cost you a lot of money. In many cases, when I'm doing regular production, I'm manufacturing some widgets and objects and so on, I make some half decent profit. But probably I cannot really afford to have top quality instruments. I just cannot afford to have that. So many times what I do is, industry in fact accepts this, that they will allow a certain amount of precision to tolerance. What is tolerance now? Tolerance is the difference between, if you see the slide, tolerance is the difference between the upper spec limit of the part that I'm trying to produce and the lower spec limit of the part. This difference is what we call the tolerance. The bias itself is sometimes measured as a percent of the tolerance. If this bias is high, this percent will be high, and of course your data would be biased, and the data would not be reflective of the true variation or the true size of the parts or the true dimensions of the parts. That's why I would like to have this bias as small as possible. Would like it to be a very small percent of the total tolerance that is there. That is the difference between the upper and the lower spec limits. Then there's something called precision to tolerance ratio. Precision, believe me, the first part was just the difference between the averages. That is how I measured my bias. But when I measure my precision, I look at gauge repeatability, that's like one variance component, and also I look at what we call gauge reproducibility. This is another component of variation. And these two together, when I got gauge repeatability, I've got gauge reproducibility, I've got two components, two contributors of variance. This is what leads to imprecision, and that is measured by what we call P, and this ratio of precision to tolerance, this also should be quite small. We'll see later that industry has set some norms there. Then of course, if I'm using a system that can shift its performance over time, I may produce some control charts, and that is to be done with some standard objects. I may take some standard objects and I may measure the dimensions of the standard objects at various points in time, and I may produce a control chart with this. And the control chart can tell me if the measurement system itself is drifting or if it is staying stable. That's something I can also do quite often by plotting various types of control charts. That's a pretty decent approach, in fact, to try to make sure that the system stays the same way as time goes by. Calibration, of course, is a way, like I mentioned, it's a way to make sure you have some idea of the inaccuracy in the system. Inaccuracy is what? It's the difference between your observed average and the true dimension. The difference between the observed average and the true dimension, this is the inaccuracy of the system. And this is something that you'd like to eliminate. And for this, what we do is, periodically we'll take a gauge. I would like to get it calibrated. So we'll submit to a standards lab, and those standards people, they will make the settings the way they are supposed to be, and they'll apply some standard voltage there, and then take a look at the gauge at various settings. At various readings, they will be checking with different amounts of voltage applied. They'll take a look at the readings there. In the process, they produce what we end up calling the calibration chart, which is what you see on the screen there. That's a calibration chart. I have master values or the true values of, let's say, voltage that I applied, and the readings, the observed readings is what I apply there. Now, obviously, ideally, of course, this line should really be at a 45-degree angle, but most often, systems are really not in proper calibration all the time. There is some inaccuracy there, and because of this, there might be some variation there. Also, you see an issue of non-linearity also. To try to take care of that, we do calibration. That's like something there that is invariably done. When you've got a good gauge, and a good gauge that is being used for research purposes, it must have a calibration chart with you. Otherwise, the data that you produce using this, it may not really end up being a good piece of data there, and there may be questions about its validity. That's like something that we'd like to minimize to the extent possible. Now, there are many different things that can lead to measurement variation. I've got a few things there. I've got the environment, I've got materials, I've got methods applied in doing the measurement itself. Then the gauge itself, it may introduce variation, and that will be the issue of repeatability. And of course, then I've got operator who introduces the issue of reproducibility. So you see there, I've listed there various factors that could lead to variation in the measured data. And of course, this is another picture of it. But what I'd like to point out to you is that the concern that industry has most of the time is the issue of repeatability, which means if I apply the same gauge on the same object again and again, will I get the same reading? The other issue that industry worries about, the issue of reproducibility. That means if I use different operators to do my gauging, will they produce numbers which are all pretty close to each other? If there is a wide variation between going to operator A to operator B to operator C, that measurement system is actually, or that measurement practice is not probably a good one. Therefore, what we would like to do is, we would like to get an idea of the total variation in the observed process, which is part due to the actual variation in the process and part of the variance that is introduced by the measurement system. And the measurement system variance itself can be split now between repeatability and reproducibility. What we would like to do is, we would like to take a look at now, a closer look at repeatability, which is caused by the gauge, and reproducibility, which is caused by the operator in regard to the total variation that is there now in the observed data. Now, this is another way to state that Pythagoras theorem that I mentioned to you earlier, the total variance of measurements. This is the total, the error, the measurement error that I see, the total error that is contributed part by reproducibility, the variance due to reproducibility, and also the variance due to repeatability. So, I have got reproducibility which is traceable to people, the operators, and repeatability which is traceable to gauges. So, I have got really, if you look at the components of the measurement system, I have the true process. I have the true process, I have got the standard objects, or I have got production objects which are being produced, and I have got to make some measurements on them. I have got to make sure I get the understanding of the real variation itself. So, I have got these objects that are being produced by the system. Now, how do I get the knowledge of what exactly are the dimensions of this or some quality characteristic? I apply some measurement system. What does the measurement system comprise? It consists of the gauge and it consists of the operator. Now, there is some variance that is contributed by the gauge, and this is captured under repeatability. And there is some variance that is contributed by the operator, and this is captured under reproducibility. And I have got to quantify both of them. I am going to show you a calculation procedure by which you can find the contribution, that is the variance contribution that is due to the gauge, and the variance contribution that is due to the operator. I am going to show that to you in a couple of minutes. Again, here is an idea of the kind of industry accepted norm for precision to tolerance ratio. Tolerance, as I told you earlier, it is the difference between the upper and lower spec limits of the part that you are trying to measure. The variance that is introduced by the measurement system, that multiplied by 5.15, sigma multiplied by 5.15, that actually captures a pretty large span, almost like 90-95% or perhaps even more of the variance that is there in the measurement system. That is totally captured if you do 5.15 multiplied by sigma ms. Ms is the measurement system. So, that gives you actually an idea of the variance that is introduced by the measurement system itself. Divide that by the tolerance, and this ratio should be of the order of 10%. The best case picture for this is 10%. An acceptable limit in some industries is 30%. Not in all industries, but some industries will accept this precision to tolerance ratio as high as 30%. What does the precision or imprecision comprise? It comprises partly the measurement error, which consists of repeatability and reproducibility, and it could also be due to stability and so on and so forth. We shall focus here between two things, in fact, we will focus on two things. One is going to be reproducibility, the other is going to be repeatability. If you look at the measurement value, if you look at measured data, that measured data consists of the true value, it consists of the inaccuracy which is really fixed by calibration, and then I've got repeatability and I've got reproducibility. These are the different factors that impact the true measured value, the measured value. This is the observed measured value and the true value is here. Now, unless I have a decent idea of what these are, I'll never know what the true value is, because all that I'm observing is this. If these values are unknown or if they are large, then of course I might just think that I've got an idea of the true value, but in actual fact I don't have that because of these hidden things which are also there inside the measured value. Again, let's take a look at capability. This is like another measure of gauge R&R or the measurement systems which are there. And one of the ways to do that is you take the standard deviation of the measurement system, multiply that by 100 and divide that by the observed process variation. Observed process variation is now part to part variation as observed through a gauge. If this turns out to be small, it actually means that the measurement system itself is actually contributing very little of variation. What you see in the observed data is mostly due to the true part to part variation. This is what we would like to see. In fact, it turns out if you look at the QS9000 system, some of you might remember that the automotive industry, automotive parts suppliers, they are required to use the QS9000 system to be able to supply to Ford, GM and Chrysler and also to other companies, large truck manufacturers and so on. It is said, it is actually held by the automotive industry, those who really get QS9000 type part supplier, that this ratio, this capability should be 6% or less. That is the extent to which I can allow the measurement system to be slightly off. Otherwise, I should not be using that measurement system there. Now, how do we find repeatability as an example? Let's take a look at how we find repeatability. Then we'll also take a look at how we find reproducibility. And you can see the slide here, which actually is using now EV as the notation for what we call the variance due to repeatability. These are the different readings that are obtained by the same gauge, by the same operator. There are some variations there, and that whole thing is quantified as a variance, and this is called the equipment or gauge variation. How do we actually find this? I'll be showing you a couple of points here. Remember, my old picture was like this. I have a total variation. I have this total variation which is partly due to the operators, partly due to the gauge and partly of course due to the true part. These three, they contribute to this total variation. What ideally I would like to see is, this total variation to be comprising only of part variation. But what happens in real world? I am using a real gauge which has got some repeatability problem. I've also got a bunch of operators, they are contributing their reproducibility variance. So what I observe there is partly due to this, and of course then I've got this true variation, part to part variation also there. Right now I'm going to be telling you how to get an estimate of this. This is the issue of repeatability. Let's come back to the screen here again, and I have here what we call repeatability. And notice here the formula shows here that sigma is the standard deviation in gauge to gauge measurement, repeated measurements, application of the same gauge. What is this quantity called R bar to the right? I'm going to show you some real data also, and therefore you'll be able to get an idea of the real data right away. But let's say I've made some measurements. With the same gauge I've made some measurements, and I'm the single operator. I've made some measurements using the same gauge, and my readings are x1, x2, x3, x4, x5. Let's say I've made 5 measurements. Now range, which is also called R, of the data that I've measured here is the difference between the largest one, this is the max data value, and the min data value. So what does this R comprise now? x2 minus x4. That is the range of my measured data. That's the range of my measured data. And if these data, if they are repeated application of the gauge on the same object, I have information here which is really going to capture my repeatability. So this is going to give you repeatability. This is now application of the same gauge on the same part. I apply the same gauge on the same part repeatedly, and I take readings. And I write them down. Those readings turn out to be x1, x2, x3, x4, x5, as I've shown here. These readings, they are individual readings, but they have slight variation, and that variation is really due to repeatability. So this is an issue here. What did I find here? I found the value of R. How do I get sigma? How do I get sigma out of R? I am just going to call this sigma repeatability. This will be equal to, you take many such readings and you take many such samples, you will end up with R1, R2, R3, R4 and so on. So, you have like an R bar. R bar is the average range that you found in many such measurements that are done, perhaps on different parts, but again each part is measured 5 times or n number of times, and from that you find your R. How many times you measure is very important, because that will give you an idea of n. N is the number of times you have measured the same part. So, here n in our case is equal to 5. N in our case is equal to 5. To try to find sigma, what I do, I divide that R bar, which is the average of such repeated estimates of the range. I divide that guy by a quantity called D2. D2 is a quantity. This is the formula. This is the formula which allows you to start from range. It allows you to start from a quantity called range, which is this quantity, and it allows you to determine this quantity. Of course, the unknown here is D2. What does D2 depend on? D2 is a constant. D2 depends on, this is dependent on n. N your number of times you made measurements. And let me show you how this is done. I have the formula on the screen here, and notice here I say sigma repeatability is equal to R bar divided by D2. These R bar now, they are the average of every part has been measured a certain number of times, and I've taken an average of that, and I've got this thing. Now, suppose I've got P such R bars found, P such R bars found, then of course I'll have a R double bar, and therefore I've got an estimate here which is the average R bar. Once I have that, all I need is the value of D2, and D2 depends on the number of times I've made my measurements on each part. So, when I do that, I actually have a table. I have a table, and this table I am showing you here, the number of observations in a sample. What is a sample? A sample, again, like I mentioned to you in the chart that I was showing you, the diagram that I was showing you, x1, x2, x3, x4, x5. There are 5 measurements there. Therefore, the number of observations I have made here is 5. N is equal to 5 there, as I put down here. This n is used on this chart here, and I use that right here, and I read off the value of D2. So, D2 in our case is going to be 2.326. 2.326. So, the value of D2 here is going to be actually 2.326. That's going to be a value of D2, and of course, I've got my R bar on top. This is going to give me an idea of sigma. Sigma is what I'm after. And what is this sigma due to? This sigma is due to the gauge. This sigma is due to what we call repeatability. That's what this is for. So, now you have an idea how I can go from repeated measurements to the calculation of R bar, and then I use the information about D2 to get my sigma. And this sigma is a very important one. It gives me an idea of what is the amount of variation that is actually contributed by what we call the gauge, applied repeatedly on the same object. I have now the other dimension, and in this case what I have done is now I am talking about reproducibility. And try to recall, reproducibility is caused by the operator. Repeatability is caused by the gauge, it is caused by the gauge, and reproducibility is caused by the operator. Now, one person using the same gauge will probably not introduce much of an error. That is captured under what we call repeatability. But if there are multiple individuals and they are using the same gauge and producing different readings, then it's an issue of reproducibility. People are not able to reproduce what somebody else did. I must have an idea of that also. So, for that what I do, I set up a table and I get different operators. I am going to show you that table in a minute. I am going to ask different operators to make measurements, and from that I try to again calculate averages, average for each person. If these averages differ from each other, again I have got a range of data. And again I can utilize the same formula, the same D2 type formula, and I am going to get an idea of what I call this time sigma reproducibility. And that is given by the formula which is in the gray box here. The gray box basically says the standard deviation for reproducibility, and this is also called appraiser availability, because appraiser is the inspector. appraisal variability is AV, which is equal to this. You look at the standard deviation of that, that is equal to R X double bar. And I'm going to tell you exactly what that X double bar in a minute, divided by D2. This D2 is different from the D2 that I used before. So this D2 should not be confused with the D2 that I used before. The first D2 actually comprised, it came from the number of times I repeated my measurements using the same gauge. I measured the same part n number of times. And here I've got different operators. So I've got P different operators. And notice here I've got P there. P different operators, they've used the same gauge and they produced readings. Okay, what are the readings like? When I look at the readings, I look at the X bar value. And within X bar value, I'll end up with, if I show you the real data, you'll probably get a real good idea of how I go about doing this. So I'm going to come back to this formula again. I'm going to come back to this formula in a couple of minutes. Let's go and see what real data looks like. Say I've got a caliper and I produce my data there. I use this and I apply my data. And here's some data. Now I'm going to have a cleaner display of the same data there. Let's just take a look at what kind of things we've got in this. We've got two sets of parts. Actually, it's the same part. I've got 5 parts. Part number 1, part number 2, part number 3, part number 4, part number 5. And I ask operator A to repeat the measurements on part 1 3 times. Repeat the same kind of reading on part 2 3 times. Repeat the readings of part 3 3 times, and so on and so forth. Then I take the same parts and I know exactly which exactly those parts are. What is the identification? I know that. So part 1 here is again given to another operator. Part 1 is given to operator B, and he makes 3 measurements there. And again he makes 3 measurements of part 2, 3 measurements of part 3, and so on and so forth. Now notice something here. Notice a couple of things. There are variations in what we call reading to reading. Reading to reading, there is a variation measured by the same operator on the same part. What would this be attributed to? This is the repeated application of the gauge. So this will give me an idea of repeatability. And now if I work out the overall average of all this, I'll get an idea. If I compare that for operator A to operator B, I'll get an idea of what we call reproducibility. And we'll show that to you the moment I convert this into a sheet that I can start doing this thing. Now this is just a pictorial view of what we showed you earlier. I have that data there in a table. Now this is just a pictorial view of it. What is this now? What is this point? This is actually the range of measurements done on part 1. This is the range of readings taken by operator A on part 2. This is the range of, and we're going to be verifying this. Let's look at this thing, for example. Let's look at the first one. The first column is supposed to be readings taken by operator A of part 1. And the range here is indicated as 1. Let's go back to the data. I'll look at the data again. The max value of the readings is 517. Min value is 516. The difference of that is 1. And that is exactly what I've got here. I've got 1 as the gauge there, as the reading there. Look at part 2. Range is given here as 4. Let's go back and see what the data says. I see the max value as 520 and the min value is 516. The difference between these two is 4. So the range here was 1, range here is 4, range here is 1 again, range here is 2, range here is going to be the difference between 520 and 516, that is 4. It is 4 here, and 1 here, and 4 here, and 0. The fifth set of data, that is, these are measurements taken on part 5 by operator B. It has no range. Let's take a look at that chart here again. It's got no range. Once I have this data, this is the average and it's staying right there. Once I have this data, I'll take a look at some of the averages also. First of all, I try to find out the range in each of these cases. I've got the range calculations done. And because the data is given here, the range calculations are not going to be very different. Now, if I look at this quantity here, that is the average of the readings taken on part 1. These are the average of the readings taken on part 2, part 3, part 4, and so on and so forth. There is an overall effect, overall value for this average. these averages there is an overall average there, and that turns out to be 516.33. Now that average is the average which has now got a couple of things cancelled out. One, it has got the gauge to application, reading to reading variation that is applied by the gauge, that is produced by the gauge. So that has been averaged out by this, and also I've averaged out the difference across parts. So I've got this data here has been adjusted for both. It has got the part to part variation cancelled out, and also gauge to gauge variation has been cancelled out. It's very, very important that we do this. It's absolutely important. It's got part to part variation that is there. Part to part variation has been neutralized by summing across, and of course gauge to gauge variation has been also averaged out by doing this. Now this is the overall average that is produced by the operator. It turns out operator B produces, operator 2 produces a different reading there. Now the difference between these two readings is really attributable only to the difference between the two operators. Therefore this would give me an idea now the variation that is attributable to reproducibility, and we'll take a look at that. The gauge effect, that is actually the average of the ranges there. So the average of the ranges is right there. I got the gauge there, gauge reading there, and I've got the gauge reading here also. So actually if I average out these two, that 2.5 number is going to be the gauge effect contribution, and the difference between this number and this number, that's going to be the effect of the operator. How do I do that? Let's take a look at the calculations done. Repeatability, that is the contribution due to the gauge system itself, and I have two readings here, and I'll show you exactly where these readings came from. These readings came from the R value, R bar value, the range value that I produced by the gauge. And remember now this is the average of all these different ranges, and these ranges were there because in each of these repeated readings I ended up with a variation. Ended up with a variation there, ended up with a variation there, and a variation there, and a variation there. And when I average these out, I get the idea of the contribution due to the gauge there. I do the same thing for the other part. I end up with 2.6 as the effect of the gauge there. If I look at the calculations here now, R double bar, which is now the overall average of the range calculations there, the range calculation 1 and range calculation 2. This is going to capture the effect of the gauge, and that's what I've got captured there. When I divide that by D2, this D2 would have come this time from R. Why R? Because I applied the gauge 3 times. When I calculated my R. My R calculation came actually from the variation of these 3 gauges there, and that's what I've got there. If I go back to the calculation again, these 3 measurements, they led to my estimate of my sigma repeatability. That's the standard deviation of repeatability. That's caused by the gauge. Reproducibility would come by when I look at the X double bar on one side and X double bar on the other side, and I divide that. This is now a range, and this range is attributable right now to the two operators, and therefore this D2 would have to be dependent on P equal to 2, and I go back to the table again and I can actually do that. Let's take a look at D2 here. D2, the value that I've used here is 1.128, and that should correspond to my value of N to be equal to, which in this case is P, to be equal to 2. Let's go back to the table there of D2, and here's the D2 table there. Notice there for sample size equal to 2, I've got 1.128, and for sample size equal to 3, which is the attributable to the gauge, it turns out to be 1.693, and this is what I've got shown there. I have for R equal to 3 or a sample of size 3 taken, that turns out to be 1.693, and that's what I got there. Now this is the sigma now that is attributable now to the gauge, and this is repeatability, and reproducibility would come, the estimate for that is going to be this. So in this case, if I want to get an idea of the total variance contributed by my gauge, which is the repeatability contribution, and my operators, which is the reproducibility contribution, I'd have sigma square measurement error, the total measurement error, contributed part by the gauge and part by the operator. And those, if you square these quantities there, square this quantity and square this quantity, you end up with 0.596 plus 2.181, that is 2.776. That's the contribution by the gauge R&R, which is the gauge reproducibility and repeatability not being perfect. Ideally, this should be 0, but it is not so. Therefore, the total variation now, the total variation was found by going back to the gauge, going back to the total overall data, and I found out the overall variation, and I call that the total variation. That's contributed in part by the part variation, part 1, 2, 3, 4, 5, part due to the operator and part due to the gauge. With these three different contributors of variance, when they are added up, we end up with the sigma total that turns out to be this. Now, if gauge variance is so much, if I subtract this quantity from this quantity, we'll end up with the part to part variation. This is what I'm really after. I'm really after part to part variation, which I've captured like this. Now, there are some other ratios also which are used by industry. For example, this is exactly the same formula that we had there before. The only thing we've done here is we've got the estimate of the variation that is contributed by equipment and also by the operator. So, those we've got there, and this precision to tolerance ratio, this is also shown here. This is also very important. In this case, instead of that 5-point number, I've used a 6-point number. So, slightly wider, and this is also used by many industries. The upper spec limit and lower spec limit, these of course come to the specification of the part itself or the product itself. Again, if you look at this ratio there, that is the sigma contributed by gauge R&R divided by the sigma, the sigma of the true part variation. This ratio should be less than 10%. It should not be much. It should be less than 10%. So, therefore, again the total picture is going to be like this. Part variation, this is what I am really after, is distorted by the operator cost variation in the data and also the gauge cost variation in the data. So, what I observe in the readings of a gauge is this, and I've got to estimate these two quantities in order for me to get an idea by difference between this and the sum of these two quantities to get an idea of the true part to part variation. This is very important. And of course, the industry has, I've given a couple of slides. Industry has its own way to specify these things when it comes to real use of the real measurement system. So, to try to tell you again, reproducibility is due to operator, and how can you improve it? It could be through training, it could be through really going through the procedures over and over again and again to make sure that they understand what they have to do, and they should contribute as little as they can. They should really act like each other. Repeatability, that would come through gauge maintenance and also the thing. Now, notice here I have not used calibration. Calibration impacts accuracy. Calibration does not impact precision. Gauge reproducibility and gauge repeatability, these have to do with variation, and that has to be really taken care of when you look at the variation. Variation is what we are looking at. So, if I look at my total picture here again, I am really, when it comes to precision, I am looking at the total variation, which is contributed part by the part, in part by the parts that I am trying to measure of the process, and part due to operator, part due to the gauge. And of course, to try to improve this, you could apply the DMAT procedure. That's like one way. I've given you some details there that you could take a look at. Industry has come up with some specific guidelines, and automotive industry people, particularly the guys who make cars, they've come up with their own system, and they use a slightly different calculation procedure. And I've given you the slides there, and in place of using D2, they use two other factors called K1 and K2. But exactly, the procedure is exactly the same. And they also use the Pythagoras theorem, and they also try to get an idea of starting with the gauge, then doing some measurements with the operator. They try to get an idea of how much is the measurement system contributing to the total variance in the data. So, if you look at the total variance in the data, which is this one, how much of that is contributed by the operator, how much is contributed by the gauge, so that they get an idea of this. Ideally, they would like to have this contribution as small as possible, so that what they see is what it really is. This is what they would like to be able to see. Then there are some other metrics also which are used, and I've shown them there. And again, of course, I have given you a picture again of the data itself. And mind you, the data is a data collection scheme. Here I've got multiple operators involved, I've got two operators involved in this case. I have multiple measurements made. I use the same gauge, by the way. I use the same gauge to try to get an idea of how much is the contribution of this repeatability issue by the gauge itself. I get that. And then, of course, I try to estimate the various things using the appropriate either ranges or averages to try to get an idea of what it is. So again, I show the calculation. These are the calculations which are done by the automotive people. They are shown here. Certain cases, the measurement system itself can be totally unacceptable, and which is like when the gauge readings, they turn out to be such that are contributing almost 20% of the error. That's in the final variation you are contributing to measurement system. That's not such a good picture there. And you got to make sure your parts, which is what you are really after, those are measured correctly. Correctly means there is no inaccuracy. That means the gauges are calibrated. You've got well-trained operators, so your reproducibility system issue is as small as possible, and also you measure n times and you take the average and you try to make sure that the gauge readings, when you go from reading to reading to reading, that repeatability issue is also not quite there. And of course, there are fancy methods called ANOVA. Those can also be applied, and they can also be used to do measurement system analysis. The ultimate idea, of course, is you got to make sure that the measurement system, whatever gauges you are using plus the procedures they are using, they do not contribute much. And what you see, what you observe is exactly what the true variation is. So therefore, you can rely then on the data that you produce, because your decisions have to be data driven. I'll continue with the Six Sigma series in the next lectures. Thank you very much.